diffraction plays important role in the formation of image in microscope, telescope, etc. So any optical equipment, we collect the diffraction, you know, the diffracted light. So diffraction is inevitable in the imaging. So we have to understand the phenomenon, otherwise you will not be able to utilize it. Now this is one, and there is another very important, applications of the phenomena of diffractions, like who do research activities. For example, we do research in the area of nanoscience. In our lab, you can see the web that we have nanoscience laboratory under physics department. So where my student, they do a lot of work in the area of nanomaterial, the prepare materials and study their optical, because I do research in the area of optical field photonics. So there, and also other people also do research in the nanoscience, not only our group, but other groups are also working here in NIT Durgapur. So when you prepare a material, not only nanomaterial, in case of the bulk, like if you grow a single crystal, then you need to understand the phase, what is the phase of the material. Then X-ray diffraction is a technique by which you can do that. So the microstructure, such as phase of the crystalline material, can be determined. The second applications of the phenomena, very important application, scientific and microstructure of crystalline materials can be determined by diffraction of X-ray. There are many industries, they have X-ray machines within their premises, because particularly the metallurgical industry, so who prepare materials, and they have to study not only this microstructure. The many other microstructure includes many things, like in case of nanomaterial, the size of the nanoparticles can be determined by X-ray, or there are other things, particularly the student from metallurgy, they will be studying in details later on. So the microstructure of crystalline materials can be determined by diffraction of X-ray. And the grain size of the particle size of nanostructured material can be determined by analyzing X-ray diffraction pattern. So these are some of the applications which I have mentioned. More will follow when we'll discuss. Now there is a thinking question given here, that why X-ray radiation is required for determination of crystal structure. Can you answer this question? Again, go back to the definition, you can answer it. So I just give you the clue. Use this definition and answer this question. Anyone? That why we need X-ray for determination of crystal structure, not the visible light or infrared light or a microwave. We need X-ray.
Order of wavelength is very similar to the crystal structure. It's very small.
Yeah, Anu is saying something.
Sir, so the order of the wavelength of X-ray is very small, which is similar to the crystal structure.
Your voice was low. You tell that X-ray is small and something.
Yes, sir. The wavelength is very similar to the size of the crystal structures. That's why.
Okay, good. Any other answer from anyone? Someone else was telling something. No. Okay. So basically, as Anu was telling, that the crystal structure, that is, for example, the spacing between the two atoms, or that is the lattice constant, we say, that is of the order of X-ray region, isn't it? Or of the order of angstrom. The lattice constant is of the order of angstrom, few angstrom. So that is in the X-ray region. So for diffraction phenomenon to occur, you need wavelength of that order, otherwise diffraction effect will not take place, and then you will not be able to see the orientations of the atom. To see the atoms, how they are organized in the lattice, we need X-ray. Okay, because for diffraction phenomena to take place, we need the wavelength comparable to the diffracting obstacle or aperture. So X-ray is required. So study it a bit further and then prepare the answer properly. And this phenomenon was first discovered in 1665. This is long back, by Grimaldi, but correct interpretation was given by Fresnel. The phenomenon of refraction can be described as the mutual interference of secondary wavelength originated from various points of the primary wavefront which are not obstructed by an obstacle. So, diffraction is some sort of interference. We'll see later on when we go to the mathematical derivations. It is somewhat an interference. But in this case, definitely this also you have studied in class 2, the difference between diffraction and interference. That in case of the interference, normally two beam superposition, we call as interference. If there is a multiple beam superpositions, then we refer to as a refraction. And basically, in case of the diffraction, the superposition of the secondary wavefront takes place. And in case of the interference, this is primary wavefront. So here that the one light incident on say n number of slits, and then they emit secondary wavefront and which superpose and produce the diffraction. So the mutual interference of secondary wavelets originated from various points of the primary wavefront. So primary wavefront, like which are not obstructed by the obstacle, definitely there is an obstacle, but the portion of the wavefront which are not obstructed by the obstacle, they re-emit secondary wavelet, and those secondary wavelets superpose and produce interference, and that is finally the diffraction pattern. So we'll understand later because we will discuss in detail. Now, again, we are continuing the second objective, that why diffraction is important. Since every optical instrument, I have already told, make use of only limited portion of the wavefront, the diffraction effect always plays important role in functioning of the optical instrument. Therefore, a clear comprehension of the nature of diffraction is of fundamental importance for a complete understanding of practically all the optical phenomena. So this I have already told. Now coming to the second objective, that what is the difference between interference and diffraction, which I was discussing. So the main differences are like this. Although it is, like Richard Feynman says that, no one has even been able to define the difference between the interference and diffraction satisfactorily. It is just a question of usage, and there is no specific and an important physical difference between them. The best we can do is, roughly speaking, is to say that when there are only a few sources, say two, interfering, then the result is usually called interference. But if there is a large number of them, it seems that the word diffraction is more often used. So that is the saying of Richard Feynman. You can read the volume 1 Feynman lecture on physics, volume 1. Otherwise, we can define the difference like this. In interference, superposition of light wave coming from the same source takes place. Here, the light wave coming from different portion of the same wavefront, like primary wavefront, takes place. In the width of the interference, like that interference between secondary wavefront, but they are coming from the primary wavefront. The width of the interference fringe may or may not be uniform. So this is a significant point. But in case of the diffraction, fringes are unequal width. So in case of the diffraction, the fringes are of unequal width. Always. All bright bands are of equal intensity, but here it may not. All bright bands are not of the same intensity, and the intensity depends on the ordered number of the fringe. So this is another significant difference. Region of dark bands are perfectly dark. Region of dark bands are not perfectly dark all the time. So these are the sum of the differences we can write down. Now coming to the next objective, that is classification of the phenomena of diffraction. Now the phenomena of diffractions are classified into two categories depending upon the geometry of the experimental setup. They are Fresnel diffraction or Fraunhofer diffraction. So there are two. So as shown in the diagram below, the Fresnel setup and the Fraunhofer setup. Now while observing a diffraction phenomenon, you need at least the three objects. One is the source of the light, and another is a diffracting object that can be a slit or anything which diffract the light having size comparable to the wavelength of the light coming from the source, and a screen. These are the minimum three things required. Now, if the slit or the screen both are at finite distance from the source, then it is a Fresnel diffraction. So both the slit and the screen, or the source of the light and the screen, are at finite distance from the plane of the slit, then you have a Fresnel diffraction. And as a result, here the wavefront will be, in the Fresnel diffraction, due to the diffraction is formed due to diffraction of spherical or cylindrical wavefront at the edge of the obstacle or aperture, and observing screen is kept at a small distance away from the obstacle. Here lenses are not required. So here either the spherical wavefront or cylindrical wavefront is used because your screen is at a finite distance from the slit and the source is also at a finite distance from the slit. But in case of the Fraunhofer diffraction, the source of the light and the screen are at a large distance from the slit. So in practically to perform the experiments, we use lenses. So in the Fraunhofer class, diffraction pattern are formed due to diffraction of planar wavefront because they are coming from the long distance, so they become planar. And in this case, both the source of the light and the observation screen are kept at infinite distance A from the reflecting aperture, and here lenses are required to demonstrate the experiment. So this is the setup. So you have a source of light and then the lens which make the beam parallel and incident on the slit, and then again the lights are diffracted and you can collect the light on the screen by using another lens, and the screen usually kept at a certain distance, the focal point of the lens, for example, and here you get the diffraction pattern. Now, so both the cases, like here the plane wavefront, here also the planar wavefront are incident on the screen. So the interference between planar wavefront is taking place in case of the Fraunhofer class diffraction. So you need the lenses to do the experiment. So these are the differences, please remember. Now I'm coming to the last part of the objective of today's class, that is calculation of resultant of n simple harmonic vibration. Now this can be a mathematical problem. So before going to that, let us discuss the physics here, that how to produce n simple harmonic vibrations having phase in arithmetic progressions. Let you have an n number of slits, 1, 2, 3, n, which are separated by equal distance, say d. The slits are separated by equal distance d, and 1 and nth slit are separated by distance capital D. And a plane wavefront, a plane monochromatic light of wavelength lambda incident on this array of n fine slits of equal width. The separation is d and the spacing between first and nth slit is capital D, as I have already told and also shown in the figure. Now according to the Huygens principle, on incidence of the wavefront, as soon as the wavefront incident on the slit, each part will act as each part of the slit will now act as the source of spherical secondary wavelet, and they will be at the same phase because they are part of the same wavefront. And those wavelets superpose at the point P of the screen, and they will produce secondary wavelets each point of the slit, and those secondary wavelets will superpose at the point P of the screen as shown in the figure. Now since point P is at a far distance from the slit, the variation of amplitude of the superposing wave may be neglected. So we'll ignore the variation in amplitude because they are at a large distance, so assume all are having same amplitude. But their phase will not be the same. Now let us assume that we are collecting light, a plane parallel beam of light, which are a parallel beam of light which are diffracting all at an angle theta. Now theta can vary, so accordingly the point P will vary. So let the light which are coming at angle theta, they meet at the point P. So let us calculate that, let us write that the disturbance which reach the point P at the time t coming from the ith slit is real part of this, say a cos kx minus omega t, which we have written as a cos kxi minus omega t, which is coming from ith slit. So a cos kx minus omega t, which we have written a to the power I kxi minus omega t, the real part of it is cos kxi minus omega t. A is the amplitude and xi is the distance of the point P from the ith slit. We have used exponential here to make the calculations a little easier. But the amplitude, please remember, is the real part of this. Now there are n such waves which have superposed at the point P coming from the slit number 1, 2, n, capital N, and all such waves are the same amplitude, but the phase of the waves are phi 1, phi 2, phi 3, phi n. Now the difference between the phase between the light coming from two consecutive slits, for example, the slit number 1 and slit number 2. What is the difference? There is a path difference. Is this, that is d sine theta. The path difference between the light ray coming from the slit 1 and slit 2 is d sine theta. So phase difference is 2 pi by lambda d sine theta. So the phase difference between 1 and 2 is 2 pi by lambda small d sine theta. Between 1 and 3, 2 pi by lambda 2 d sine theta. between 1 and n 2 pi by lambda, capital D sine theta. Capital D is n minus 1 into small d. So we get alpha, that the phase difference between the light coming from two consecutive slits is 2 pi by lambda d sine theta. So we can write the psi as, at the point P, the resultant will be the linear sum from the principle of superposition. So resultant disturbance is a to the power minus I omega t. We take common from all, and then e to the power I kxi, that is e to the power I phi I, that is phi 1 plus e to the power I phi 2 and dot dot e to the power I phi n. Now if we take common phi 1 to the power I phi 1 from the bracketed term, then it becomes a to the power minus I omega t to the power I phi 1, and then 1 plus e to the power I phi 2 minus phi 1 to the power I phi 3 minus phi 1 and dot dot I to the power I phi n minus phi 1. Now you see the capital D can be written as n minus 1 into d. Say n is equal to 2, then this d become d. Say there are 1 and 2 slits, then distance is d. If there are 2 slits, there are 3 slits, n is equal to 3, you get 2d, and so on. So you can write capital D as in general n minus 1 into d. So phi n minus phi 1 is 2 pi by lambda into capital D sine theta. So 2 pi by lambda into n minus 1 into small d sine theta. So this is basically n minus 1 into alpha. So phi n minus phi 1 is n minus 1 into alpha. So basically, this is e to the power I alpha. So you can understand that this is a GP series with a common ratio to the power I alpha. So there is a GP series 1 plus e to the power I alpha plus e to the power I2 alpha and so on. And then the sum of this series is this e to the power In alpha minus 1 by e to the power I alpha minus 1 e to the power I phi 1 minus omega t. So a to the power I phi 1 minus omega t, and then you take common to the power I n alpha by 2 from the numerator and to the power I alpha by 2 from the denominator. Then you get to the power I n alpha by 2 minus e to the power minus I n alpha by 2. And here we will get to the power I alpha by 2 minus e to the power minus I alpha by 2. Now if we use Euler's formula, e to the power I theta plus minus I theta is cos theta plus minus I sin theta, then this become 2I sin n alpha by 2 and denominator become 2I sin alpha by 2. So, and e to the power I n minus 1 into alpha by 2 from here, and to the power I omega 1 phi 1 minus omega t and a. So psi become this. Psi become this, and then 2I will cancel out, and ultimately we rewrite, and it's become a to the power minus I omega t e to the power I phi 1 plus phi n minus phi 1 by 2 sin n alpha by 2 by sin alpha by 2. Now this is phi n plus phi I, phi n plus phi I by 2, phi 1 by 2, phi n plus phi 1 by 2, which is written as phi average. Phi n plus phi 1 by 2 is written as phi average, basically a constant. So a to the power I phi average minus omega t sin alpha by 2. So you understand the resultant of the n such simple harmonic vibrations of equal amplitude and the phase arithmetic progression is also a wave, but having frequency omega, but its amplitude is a sin n alpha by 2 by sin alpha by 2. Amplitude is now a function of the theta. So because alpha depends on theta, as you know, 2 pi by lambda d sin theta. So the amplitude of the resultant wave is a sin n alpha by 2 by sin alpha by 2. So the R is equal to a sin n alpha by 2. So the substitute the value of alpha. So half n 2 pi by lambda small d sin theta. And here sine half 2 pi by lambda d sin theta. So ultimately you get the amplitude as R is equal to a sin n pi by lambda capital D sin theta by n minus 1 by sin a pi by lambda into d sin theta by n minus 1 in terms of the capital D. So this is the resultant amplitude, or the amplitude of the wave which is produced as a resultant of n simple harmonic vibration. So this we will be using, actually this we will be using in the next class. Or from these equations, you can get the single slit diffraction, double slit and n slit. So I'll be discussing how to do that. So today we'll stop here because already time is nearing. Now let me summarize that what we have discussed. That was the objective. Up to that was the objective in today's class. So first the definition of the term diffraction, and then the application of the phenomena of diffraction, the classifications of the phenomena of diffraction, and the calculation of the sum of n simple harmonic vibrations with the phase in arithmetic progression. Now, if you have any questions, I can take one or two, and then we'll go for the attendance. If you have any question, you can ask now. Any question or the doubt? Anyone? Did you follow it?
Sir, what is the shape of the fringes in this diffraction pattern?
Sorry, once again, can you repeat?
Sir, what is the shape of the fringes produced?
Shape of the fringe. You are asking the shape of the fringe?
Yes, sir.
Yeah, we'll be dealing with that in next classes. So please wait till that. So because it depends on your experimental setup. Okay. Any other question?
Sir, for diffraction, if we use gamma ray or alpha ray instead of X ray, then what will happen?
Yeah. So give the answer from here. Now for the refraction, what do you need? You need your wavelength should be comparable to the size of the aperture. Now, for example, let me give you a classical example. Like there is a door and you are passing through the door. Do you need to bend your body? If the door is sufficiently wide enough, do you need to bend? No, we don't need. Like we travel through an open space, do you need to bend our body to travel? No. So there will be no diffraction if the wavelength is smaller than the size of the aperture, then there will be no diffraction. Okay. Diffraction will occur when the wavelength become comparable. Okay. Got the point? So if you shine a gamma ray, it will penetrate the object because gamma ray has a penetrating power, as you know. Did you got the answer? And there can be other phenomenon depending upon the type, depending upon the matter, it can start interacting with the matter. Okay. So that can happen. So it depends on the material in which you are shining your ray. Yeah, any other question?
Sir,
If no, then let yeah. Yes.
sir, if the aperture size is comparable to any other wavelength of like X-ray or gamma ray or any other, then what will happen?
I did not get your question basically. If the aperture size is comparable to the wavelength, the diffraction will happen. If the size of your aperture become comparable to the light or the wave which you are shining, then diffraction will happen.
Okay, sir.
Yeah, but you see, it depends on the nature of the radiations which you are shining. It might start interacting. Okay, then some other phenomenon also will happen, not only the diffraction. So, like for example, when you passing through a market, traveling through a market, this is just common example I am giving you. Like if you meet your friend, you don't turn your body and move past him. You just started discussing, isn't it? Oh, how are you? Why you also came? I was not seeing you, like that. But a few moments before you crossed another person, you didn't have no interaction. You just pass it, bend your body and move past. So that case only diffraction type thing happened. But now it is not only the diffraction, but actually it started interaction. Whether diffraction has not happened. So it depends on material. Depends on the material. Yeah, diffraction is one phenomenon, but there can be other phenomenon too. There can be interaction between the matter and the radiation. But here we are talking about the phenomenon of diffraction. Then by the reflection, the aperture size become comparable to the wavelength of the incident rays, then there will be diffraction. Okay. Yeah. So it is not only the reflection, there can be interaction of the radiation with the matter. Different type of interaction. if it is correct. Like to find a strong legal line, you know. So it might not come, but exception also will be present along with it. Okay, okay, fine. Now let me give the attendance. Rule number one,
Present, sir.
yeah, two,
Present, sir.
three, rule number three, four,
Present, sir.
five,
Present, sir.
six,
Present, sir.
seven,
Present, sir.
eight, rule number eight,